Welcome to Spring LIB.
Okay, in this problem, we have a Compton scattering situation where we have an X-ray incident with a wavelength, and it's scattered completely backwards at an angle of 180 degrees after the scattering, sending an electron initially at rest in one direction with some momentum. We are asked to find what that momentum of the electron is after the scattering. So the best way to do this, in my opinion, is to determine the change in wavelength of the X-ray after scattering, and then find its momentum change. And then from that, we can use conservation momentum to determine what the electron momentum is. So the main equation we'll be using is the change in wavelength equation due to Compton scattering, which depends on various quantities, but most importantly, this scattering angle, theta, which we know is 180 degrees. We also need to know what the momentum of light is, and it's actually a quite simple expression. Momentum of a ray of light with a particular wavelength is simply h over lambda. So we can look at the momentum before and after and use conservation momentum to find the electron momentum. Some constants that we will need to use and need to know ahead of time are the speed of light, which is approximately 3 times 10 to the 8 meters per second, and of course Planck's constant, which is 6.626 to the negative 34th power in joule seconds. Okay, so starting up, we need to find the change in the wavelength of this X-ray using this expression, the Compton equation. And we're substituting in for the angle 180 degrees because we're assuming that this X-ray gets completely deflected backwards. So if you recall, cosine of 180 degrees is simply -1. So this equation simplifies down to this. We're given the initial wavelength. These are all constants. M is the electron mass, which actually should be included in our constants list. Electron mass, 9.1 e to the negative 31 kilograms. It's no problem. Okay, so then this calculation will simply be 0.098 e to the negative 9 meters plus 2 6.626 e to the negative 34 joule seconds. All of that over 9.1 e to the negative 31 kilograms. Speed of light, 3 times 10 to the 8 per seconds. And after doing this, we will end up with a result of 1.028 times 10 to the negative 10 meters. So this is our new lambda prime. So once we have lambda and lambda prime, we can actually get the momentum before and after. So P initial is just h over lambda using Planck's constant in the original lambda. We can write this out to be 6.76 e to the negative 24 kilogram meters per second. So this is the momentum of the X-ray before the scattering. We can similarly get the momentum after the scattering, which is simply h over lambda prime. Only really depends on the difference in the wavelength. Upon doing this, we end up with 6.44 e to the negative 24 kilogram meters per second. And if you remember, P is the initial momentum's to the right. The new momentum is to the left. All right, it's arbitrary which direction you choose them to be, but as long as they're opposite each other, that's the important part. So we can add them together, or rather subtract them, which is adding the vectors together, but noting that one of them is the opposite direction as the other. When we subtract the two quantities, we end up with resulting. Oh, of course. So it's worth noting that the total momentum change is the magnitude of P plus the magnitude of P prime, because we not only need to turn the X-ray around completely, but then also reverse its direction. That's what was confusing me a bit. So the total delta P ends up being the sum of the two magnitudes. Writing it out in the correct order. Delta P in this case has to be, its magnitude must be the initial P, the new P, sum of those momenta, which gives us a result that's larger, 1.31 e to the negative 23. We're about an order of magnitude higher now. Kilogram meters per seconds. Now, by conservation of energy, or of momentum rather, if this is the total change in momentum of the X-ray, for momentum to be conserved, this is the amount of momentum that must be transferred to the electron in the scattering event. Thus, this quantity is going to in fact be the momentum of the electron after the scattering. If we wanted to do this in a slightly different way, we could have, from lambda prime, once we know the change in wavelength, we could have determined the change in energy. We could have then found the change in energy of the electron and then found its momentum that way. But this is a more direct route. We just have to be careful that we include both the magnitude of the initial X-ray plus the new magnitude to account for the total change. All right, and that's it. Thank you very much.